It's a pleasure to be here again tonight, doing a more APAC time-friendly, I guess, or time-friendly webcast here. And we actually have a couple of updates kicking around. Obviously, we know more now than we did when we ran this, only a very short time into the event. But I'll kind of walk through, for those that aren't familiar with it, kind of walk through where we're at, what it is. These are updated slides from what we presented before. But not wholesale, I would say wholesale changes overall. The more interesting stuff as far as changes go are definitely at the end as we start to walk through some of the mitigations in play. And again, we know a whole lot more about what we're doing as far as mitigating goes. So with that, let's get into Meltdown. And look, I'm a processor geek at heart. This is definitely something that has it's been a fun week, I guess, is something I'll say. Meltdown allows attackers to read arbitrary physical memory, right? So basically, we can go in and go read memory from anything up to and including the kernel from an unprivileged user process. This is really, really slick for us because it allows us from that user process to basically go in and identify for an unprivileged user process, go in and get a full dump of basically a full dump of physical memory from a machine. Now, when I say from a machine, I really mean from a Linux or OS X machine. I haven't tested this on x86 Solaris, although we'll talk about that as we go too. But Windows, because of the way it maps memory, you can't get 100% of physical memory, but pretty close, right? Bottom line, it's more than enough to execute a privilege escalation from any unprivileged process. And the way that this actually is happening is out of order instructions, right? So it turns out that because of pipelining and other processor basically optimization features, Meltdown executes, or Meltdown, the processor executes instructions out of order, right? So if it's given a set of instructions, it'll execute those, basically group those instructions together, execute them out of order, and then basically combine those. And these are instructions that the results from instruction 1, don't impact instruction 2, right? So processors are smart about pulling these instructions out and pipelining these, and basically here what we're doing is we are tricking the processor into executing these in an out of order fashion that then leaks data out through a covert channel. We'll talk more about how that happens in a minute. Meltdown was actually patched in Linux with Kaiser and KPTI. KPTI stands for Kernel Page Table Isolation, and we'll talk more about what that means in a second as well. So as we get into the ASLR, because this is actually important to understand as well, Linux implements this kernel address space layout randomization by default since basically by default since Linux, I think 4.12. Right? Now, the 64-bit address space is absolutely huge, and this is why the ASLR thing is important, because even though you may only have 8 gigs of RAM on your machine, theoretically, there's up to 16 exabytes of physical memory. You just don't know where the kernel, where those good 8 gigabytes are at. Well, obviously, this is not ideal for you. You'd like to know specifically where those are at. This allows you to basically, this will allow you to go in with ASLR. It'll go and randomize those addresses. We need a way to go and try to identify which part of the kernel or where the kernel is actually mapped into physical memory. And here we see that randomization is limited to 40 bits. Now, I know initially that sounds absolutely huge. 40 bits is well, heck, it's greater than the whole x86 address space, right? The problem here is that I don't have to go through the whole 40 bits. I just have to go inside of that 40-bit randomization, and I have to take some educated guesses inside there. And if I find any kernel memory, it's that area of the address space. It doesn't randomize it across the whole 256 terabytes. It picks an area at every boot and says, yep, let's put the kernel there. So all we have to do is guess somewhere inside there. And some experimentation shows on a machine with 8 gigs of physical memory, a 64-bit machine, even though we've got 40 bits of randomization, it's relatively easy. It's about 128 guesses, right? So probably less than you would expect, definitely less than I was going to expect there. So locating the kernel offsets to begin this dump is a relatively easy thing. Windows ASLR isn't actually much different. Not all of the kernels randomized. I mentioned a minute ago, though, that because of the way Windows Memory Manager is implemented, it's relatively unlikely that we can dump the entire physical address space because basically of the way that memory gets mapped in the kernel and how it's visible or not supposed to be visible, but actually is, because of this bug, visible from user space. So on an unpatched Windows system, most of kernel memory can be read, probably not all of it. Look, again, I don't know that this is a useful distinction. I'm not sure this is an important distinction, because at the end of the day, we can get more than enough data to perform privilege escalation on Windows, and from there, once you're in system mode, you can do whatever you need to. Right? So let's talk about page tables very briefly. These page tables, and this actually becomes important in a minute, contain the mappings between virtual memory and physical memory. Now, the virtual memory is used by processes, physical memory is used by the memory manager. For performance reasons, most modern operating systems, they actually map the kernel into user space, even though you can't see it. Now, technically, from a user space, an unprivileged process, sometimes folks refer to these as ring 3, you can't access physical memory in ring 0. Totally makes sense, because actually it's controlled by something called a descriptor privilege level, or a DPL. Now, when we run into this issue here with Meltdown, one of the things that we're doing is we're actually trying to read into the kernel, and I'll walk you through how this works in a minute. We're actually going to cause an exception. And so again, under normal circumstances, the kernel memory can't ever be read. This is actually going to cause a hard fault in the basically a hard fault in the processor, and basically it'll roll back any read or any transaction. So we technically still, even with this vulnerability, can't read it, but we'll show you how effectively we can leak that data out through a side channel attack. So let's kind of step through this here, and it's important to understand that we've got a CPU cache basically set up down here. We want to go read data out of basically from user memory. We're going to, and executing our process, again, this is an unprivileged process. And basically, the first thing that we're going to do is we're going to go grab a byte of arbitrary kernel memory. So we've got an address in mind, and we're going to say, hey, we want to go grab this byte of memory. And let's say that the first byte is a capital A. It's a hex 41, right? So what we're going to do there is basically we've got a user space array that's mapped here. Now, this user space array, we make sure that this is actually an array of 256 4K elements. This piece is important because these 4K is conveniently the size of a memory page in Windows. Right? Technically, it's kind of built into the processor, but Windows uses the default page size because it is by far the most efficient. And so what we see then effectively is that with the CPU cache, basically we're going to read our data in from this secret data. And again, I mentioned here the secret data. The first byte that we're going to read is basically a capital A, and we're going to go read that capital A. And then inside this code here in the out of order instructions, again, now mind you, this is going to trigger a fault. We're going to force it to write into the cache of this user space array. All right, so that's step one. So step one here, we've got this array cleared, and we know that we're going to basically go read this. Now, we're going to wrap this in an exception handler so that ultimately our program doesn't crash. So that the exception handler or process is just going to crash. So at this point, we've read the data out. Right? Now, remember I talked to you about the fact that here this user space array is an array of 256. Now, that's because there's 256 potential byte values, 256 4K elements. Now, we don't just do 256 1 byte elements because that would all sit in the same 4K page, and the CPU cache is going to load up, basically is going to cache those, and that would cache the whole array instead of just one element of the array. And so what ends up happening here then effectively is the secret data is read, and because it writes into the user space array, in order to write there, it has to go and grab one of those offsets. So one of those 4K pages, the CPU has to go grab. And when it does that, it puts it into the CPU cache. Now, it's important to know that technically we'll never be able to read the value out of the CPU cache. We'll never be able to actually read it out of this user space array. So it takes that A, and again, we're just going to write some data into offset A of the array. again, we'll never be able to read that data. That's okay, right? Because ultimately, again, we're going to see the exception. The processor is going to roll that transaction back effectively. Technically, it's not a transaction, but close enough. Although actually, with Intel, you can indeed do transactions. So alas, bottom line, it's going to roll that back so we can never read the data. But that's not important to us because in writing the data, we've actually put this one element, right? Basically put this one element of the array into the cache. Okay, so step 3 here, this exception's triggered and the processor says, hey, we executed these out of order. We never should have done this. That was horrible. Let's go ahead and flush any of that data. Make sure that we didn't do anything basically that would compromise any of kernel memory. At this point, we come back and in step 4, we begin reading through basically going and reading through memory. Now, I said before, I said a capital A, which is hex 401. I forgot I used 3.1 in this instance, but you get the idea. Basically, what we're going to do is we're going to come back, we're going to execute a tight loop here, and we're going to say for 0 to 255, return the minimum time to read an array element. And what we're going to do here is we're going to say 0, 1, 2, 3, 4, slow, 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 right? And it says slow, 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 and then all of a sudden, bam, hex 3.1, right? So hex 3.1 is fast. That cache hit tells us that that first byte was actually the hex 3.1, and now I'm at a loss to remember what hex 3.1 is, but you get the idea here, right? We can read any arbitrary data out, and basically we're going to rinse and repeat this for each byte in kernel memory. So once we've identified where kernel memory is at, we're going to walk through these 4 steps again. Basically, step 1, clear the cache. Step 2, read the data and write a piece of data to whatever offset in our user space array actually represents the byte value. That's going to force that data, that one 4K page, to be loaded into cache. Now, step 3, we don't have to do anything here. The processor is going to handle it for us. It's going to say, whoa, exception, roll that back. And ultimately, it's going to discard anything that it's done there in those out of order instructions. But because the CPU cache hasn't been cleared, we're now then able to go back and go read out of the cache and determine which page, or sorry, which byte, what the value of the byte was by which page is loaded into the CPU cache, right? So whatever this fastest read is, because memory is slow compared to the CPU, very, very slow, orders of magnitude slower compared to the cache itself. Okay, so how do we fix this? It turns out that this was actually already fixed before, I say already fixed. This was in the process of being fixed for something else, right? So some people call this the Kaiser patch, right? Or kernel page table isolation, right? And what's happening here effectively is that if we come back over here to our example of user and kernel space memory, they're not patching the out of order instructions. What they are patching here is basically they're saying, while you're in user space, we're going to map all of the basically all the virtual to physical addresses in your user space process, but we're not going to map anything in the kernel space. And by not mapping anything in the kernel space, even though you can try and say, let me go read from the kernel, the processor can't actually translate that address. And as a result, it can't actually read the data. Now, how do you actually transition to the kernel? Well, again, this is where as the transition to the kernel happens, then they'll dynamically map those pages back in before returning to user space, they'll remove them. And so this KPTI and kernel page table isolation, right? This KPTI / some people again are calling it the Kaiser patch based on some work with kernel ASLR. And basically, because the kernel memory is no longer mapped, it can't be read by Meltdown. Now, look, why do we ever map all the pages into user space in the first place? And the answer is because it's fast. It's the right way. What's right and what's wrong has kind of changed over the last week, and I'm using air quotes around right. But look, because the kernel memory isn't mapped, can't be read by Meltdown, we did this originally, OS designers did this originally because it was the fastest way, basically the fastest way to do things, right? So smart in this case until we get the side channel attack, and now it's no longer smart. right? So again, we are going to see a non-negligible performance impact, and we'll talk more about that in a little bit. Okay, so again, I have to tell you, unfortunately, that some of kernel memory has to still be loaded into user space processes, because there are times that you're going to end up getting an interrupt, right, an actual hardware interrupt, and that interrupt handler has to fire. The CPU has to be able to go reference that memory. And if you happen to be in user space when the hardware interrupt fires, how could it actually address? Well, it turns out all the interrupt handlers are all in kernel space memory. So there's a trade-off here. When we say that we've pulled all of kernel space memory out, that's not technically true. The kernel memory, some of these for the interrupt handler has to be mapped in. And look, I suspect here that a lot of our research is going to involve in the future trying to determine, because we may still be able to leak some of these addresses out, the interrupt handlers, certainly today you can. And as you leak these interrupt handlers out in kernel memory, can you use that knowledge, the knowledge that you gain, right? So don't picture this as a single attack. Picture now that we're leaking out an interrupt handler, and then we're analyzing the data we get back from the interrupt handler, and then saying, hey, based on this data, can we go through then and find other, basically go find other addresses, right? And if we can, then great, right? At that point, potentially we can still do some nastiness to the system, right? So I have to be very clear. This KPTI and Kaiser thing does not address the core vulnerability, right? And it's an important thing to recognize. Now, Intel has some patches here that probably will address the core vulnerability. KPTI does not. It does prevent practical exploitation in the way we talked about here. The kernel space addresses are just not mapped anymore. There's nothing to look at, right? Or I say nothing, except for the interrupt handlers, there's nothing to look at. Okay, so there's a rumor this is Intel only. I think we're pretty well clear past this, right? We know that it's more than just Intel. Modern Intel CPUs implement something called TSX. This is basically like a database transaction, and it does it at a hardware level. So this TSX instruction set allows you to group instructions together for all or nothing. And it turns out that this allows you to do meltdown, we'll call it meltdown on steroids. Meltdown much faster than we would without TSX. So it turns out that, again, this is phenomenally faster. And so people talked about, I think this gets around 500 kilobytes per second. And the exception handler, the example we walked through earlier, gets around 100 kilobytes per second. So this is about 5 times faster. Should I be concerned about this? I think the answer is, not really, right? I mean, look, whether you leak my kernel memory at 100K per second or 500K per second, I don't think that there's really a difference there. Either way, it's still bad, right? So again, 5 times longer to get all my physical memory doesn't really matter. You're going to privilege escalate anyway. Are ARM and AMD? Yeah, absolutely. Meltdown exploitation is theoretically possible. The paper authors, the folks that originally discovered this, they think that this is doable. They said, look, you know, it's probably harder on ARM and AMD and probably requires more precise timing. And look, all the tests that we did, we said, hey, you know, Intel worked and ARM and AMD didn't, except we think that they're probably still vulnerable. Right, so and of course you've seen some posts from certainly some posts from Apple. Apple designs custom chips or basically commissions custom chips to be built for their iPhones. And if you have been following along, you know that iPhones are also vulnerable, right? And more specifically to Spectre, but regardless, understand here that we're looking at a relatively wide range of processors impacted. So any of the hype that, hey, not impacted by this, not even, look, everybody's having to change the way they do things, right? So okay, so let's talk about Spectre, because I thought nothing could be cooler when I read Meltdown. I'm like, there's no way you can top this. As a processor geek, I'm thinking there's no way you can top this. It turns out I was wrong. Spectre is actually way cooler. It's phenomenally cooler. It's harder to exploit. So that's the good news, right? But the geek factor is ratcheted up like 4 steps from what we saw with Meltdown. Spectre abuses 2 things that you may never have heard of before this was released, called branch prediction and speculative execution, right? And basically, there are 2 versions of Spectre. Now, when I did this webcast the other day, I I really wasn't tracking the leaking data from a remote process, right? I thought that they were talking about the theory of the ability to do it, not the actual ability to do it. Turns out, no, they were actually talking about the ability to do it. We have already seen a couple of rudimentary proof of concepts built for that, and it's terrifying. So look, Spectre is being patched out, but you have to know that when Intel says we've fixed Spectre, what they really mean is we have updated our microcode and our instruction set to make sure, basically to make sure that compiler developers can rebuild their compilers to make their code Spectre safe, for lack of a better word. Right? So this is obviously concerning to me, because now I'm thinking, I have a hard enough time getting people to take downtime to do patches. Can you imagine trying to get somebody to take downtime to go find the source code for their applications, dig it out of the vault, wherever that happens to be, and then recompile that and then redeploy that? I can't fathom how long we're going to be seeing attacks to this. Luckily, again, I'll talk about this. This is actually harder to exploit. Still possible, just harder. Okay, so let's talk about the speculative execution. Basically, what's happening here is that because processors like to execute things out of order, remember, out of order execution is what causes meltdown, or what basically allows meltdown to be exploited. What's happening here effectively is that when you hit a branch, an if-else instruction, right? We have to go through, if we're going to do out of order instructions, we have to guess which branch of that if-else is going to, are we going to go left or zig right? Right? Zag left or zig right? Now, the reality is that if we say take the if, and when the condition's evaluated, it really says do the else, then we have to discard all of the instructions that we've executed up to this point. And so on the speculative execution side, because these instructions may never really be executed, a sort of CPU snapshot is taken, right? So the CPU actually takes a snapshot of registers, actually, believe it or not, stores them in a special cache, and it says, hey, let's go ahead, and that's at the branch, and it begins executing additional instructions and says, hey, if we need to, basically, if we don't ever really execute these, roll back to the point of the branch. Now, most of the time, it turns out that it guesses the branch correctly, but if it doesn't, okay, cool, no problem, we'll just roll back. Speaking of guessing the branch correctly, how does the CPU know which side of the if-else to go execute? It turns out that based on the current execution of the program, every time it hits the branch, it actually trains the branch predictor to go in and basically go execute that, basically to go in and execute that code, right? So basically it says, hey, I saw out of the last 1,000 times we hit this address, we always took the if. The odds on time 1001 of you taking the else are really, really low. And so the CPU says, hey, we went if every other time, we should also go with if this time. Or we went else every other time, we should go else this time. So the CPU learns, and I've got that in quotes there because it's not really learning. I hope everybody understands that. Kind of like machine learning isn't learning. This is just saying, hey, we see it, it's good, we went this way before, we're going to go this way again. Now, what ends up happening here effectively is that the CPU is putting this into what they call the branch target buffer, or BTB. Now, this wouldn't actually have a huge impact for cross-process. We'll talk about this in a minute. But the branch predictor doesn't store the full address where the branch instruction is at, right? So if they indexed by the full instruction size, 4 bytes in the case of x86, 8 bytes in the case of x64, this would be no issue. It turns out that it is an issue because, well, they don't actually store the whole address, right? So they kind of shrunk down on it a little bit. Now, the CPU developers, the engineers, knew there was always the possibility that they would have collisions, right? And what do I mean by a collision? Well, let's actually talk about this first, and I'll drop back into the multi-process version in a second, right? So I don't want to put the cart before the horse. Spectre allows code executing in a victim process to access data it shouldn't have access to, stuff outside the JavaScript sandbox, all right? So this isn't JavaScript specific, but I was most worried about JavaScript exploitation. So what it allows then is basically branch, well, for cross processes, branch target injection. Now, here you're training the branch prediction algorithm to mispredict the target of that branch. This is almost certainly not remotely exploitable. What you're allowing here is one process's branch prediction to impact another process. You've probably seen this wonderful hyper-threading feature that you have on your processors. Many of you, like me, probably have it enabled because it offers you awesome performance. Something that I honestly, before I started here, I knew that before this vulnerability came out, I looked at hyper-threading. I knew hyper-threading wasn't a complete other core. I knew that they shared a lot of data between those two hyper-threads on a given core. It turns out, believe it or not, they share the same branch prediction. Right, so the same branch prediction, or the branch target buffer (BTB), is shared between multiple threads, or the two threads on basically the two hyperthreads on a core. And now, because you have effectively, because not only do they share the branch target predictor, but they also don't address by the entirety of the, basically they don't index by the entirety of the address where the branch is at, it's entirely possible to generate a collision from one process to another. So from process A, we would be, or process number 1, we would effectively be training and polluting the branch target buffer. And in process 2, we would be accessing the branch target buffer from process 1. Well, the problem here, of course, is the same thing we talked about earlier. We could force a cache hit, potentially, and leak data out of a side channel. This is, again, very, very difficult to exploit remotely. I don't think we're going to see a lot of I don't think we'll see any remote exploitation. And good news here, cross-process, basically this branch target injection, even on a local machine, requires intimate knowledge of the target process that you're attacking. So you have to have a lot of knowledge about that target process. Now, again, I'm not telling you can't do it. I'm just saying it's really hard to do. Right? So that said, right, let's continue forward here, because as we look at Spectre, right, what I'm worried about here, at least a little bit, I shouldn't say that I'm like the sky isn't falling here, right? And I want to be clear about that, but Spectre can be exploited in applications that allow code to run in the sandbox, right? So picture here that you go out on the web and you hit a site, and we've all been dealing with the coin hive, the cryptocurrency mining in the browser. Same thing going on here, right? So basically, we load up a web page, and it's got a bunch of JavaScript in it. And in this case, what could happen is the JavaScript could execute in such a way that basically we leak other data from the browser that was never intended to be given to that site, right? So we're all familiar with the whole same origin policy. That's what stops one process in a browser to basically, sorry, one tab in a browser from accessing data in another tab. Okay, so maybe one tab contains attacker code, another tab contains sensitive information, shouldn't be accessible to the attacker, but bam, what do you know it is? And if you isolate each tab in its own process, this would actually help mitigate to some extent this attack, right? So for instance, if I've got my bank stuff open in one tab, and I've got my, I go to some shady website in another tab, or I get an advertisement in another tab, I don't want tab A to be able to read from tab B. And basically isolating tabs, and we'll talk about that in a few minutes here, that will actually help mitigate in this scenario. So let's talk about the exploit scenarios. How are attackers going to use these? Look, for Meltdown, I think there's two primary uses for this. Privilege escalation and container / para-virtualization hypervisor escapes. Para-virtualization, by the way, is what we see with Zen. It's also what we see with certainly Zen is one option there. Docker is another. So if we have a container type setup there, we may find a scenario where basically the attacker is able to go and break out of that container because of the shared kernel memory between basically the host and the guest. Right. So if you're in the cloud and you're relying on Docker, and again, this should kind of concern you, right? And then local privilege escalation, of course. So in the case of privilege escalation, picture that your attacker basically has the ability to execute a process. In the case that they can execute any process, they can dump all or most of physical memory. And so with physical memory, attackers could identify password hashes. They could execute a Mimikat style attack on Windows, or they could find private keys. And look, you know, initially there were some rumors about a kernel ASLR bypass coming out, and it was really Meltdown that they were talking about. You know, yes, technically you're bypassing kernel ASLR, but that doesn't really matter, right? I mean, at the end of the day, the only reason you care about bypassing KASLR is to go execute a privilege escalation exploit. And look, we can already privilege escalate here because we can take control of physical memory, and that's just cool, right? Okay, so moving past that, as we look at container escape, again, we're targeting kernel addresses that may be shared between a container and the host kernel. Again, whether we're talking about paravirtualization with Xen or a kernel sandbox like Docker. The attacker could leak data from outside the container. That could lead to a hypervisor escape, right? How would you do this? You might leak let's say an SSH private key or other interesting data that would allow you to, I mean, again, if you've never looked at a memory dump before, oh my goodness, it's the amount of stuff in a memory dump is unreal, right? So again, we don't want to lead to a hypervisor escape there. So we talk about Spectre. You know, Spectre has probably got a couple of good uses here. The primary exploit scenario for Spectre is JavaScript executing the browser and then reading from outside of the browser sandbox. I see two probable uses here, right? One is leaking data from one browser tab to another. Even if you use isolation, process or tab isolation, there's still a possibility that because you have history and you have saved form passwords and all that stuff loaded into a browser, it's still potentially possible that the attacker could read some of that and return that. I suspect that browser developers are thinking long and hard about how to mitigate this kind of thing if your processor is, you know, well, just in general, mitigating this kind of thing, right? So the other thing that they can do is leak addresses of user space modules. Now, you know, I teach exploit dev with SANS, exploit development with SANS, and among other things. But one of the things that we deal with a lot is even when we have a browser vulnerability, whether it's a heap overflow or a use after free, one of the challenges that we have is bypassing address space like randomization. We can get code execution. The problem is understanding where to go next, right? So usually we have to basically disable data execution prevention or DEP. And that requires us to go find addresses in kernel32.dll. And Microsoft doesn't like us exploiting this stuff. And one of the things that they've done, and mad props to them, by the way, is they've gone in and randomized the address of kernel32. Well, if I can use Spectre to go leak addresses from user space here, I can find kernel32.dll. And once I find kernel32.dll, then I can go exploit my original vulnerability. So this is a spot where you can chain these vulnerabilities. Now, if you're thinking, oh, that's ridiculous, nobody does that, I have news for you. The last several, if you're not familiar with this, there's a great contest that runs every year called Pwn to Own, right? And we see Pwn to Own every year being won by folks that use chained exploits, right? So when you see that, know that again, you know, as we're dealing with that, basically what you're seeing then is with Pwn to Own, you know, ultimately folks use chained exploits all the time to bypass sandboxes. So as I look at this, I'm kind of like, yeah, I totally see somebody chaining this with another exploit, right? What about leaking browser memory in general, right? Perhaps with JavaScript and an advertisement, you could leak basic data from the browser. My real concern here is multi-factor authentication, because I don't care how many factors you have, if I can leak your session key. And so I think that this is important, but I think it's also important to keep this in perspective, because doing some tests, we think now that this is going to require a long time. And we're talking about, you know, 15, 20 some odd minutes to get a good portion of memory leaked. Now, again, I don't necessarily want to rely on, okay, it's going to take 15 minutes, because I can see my user opening up, you know, going to some video streaming site if I don't have those locked down, right, and spending an hour on one of those while they're streaming a movie illicitly, right? So I can see scenarios where this happens. I'm just kind of hoping that it doesn't happen, or nobody figures out how to make it happen immediately. Now, leaking that first byte of memory is no problem. It's knowing where to go in memory that becomes the issue. I'll also point out that Spectre is a little bit less reliable than Meltdown in most cases. With as I say, reliable meaning when you guess a byte and do it based off of timing and the cache hits, it's a little bit less reliable than Meltdown was in generating that cache hit. Right, so we think that the user is going to have to stay on a page for a long time. Hopefully, this kind of shuts down the whole, like a drive-by advertisement like we see with Flash, where it's like you saw it then exploited your browser and it was done. We think here, or I think here at least, that this is going to require significant time, and as a result, we're not going to see. And I was worried about this before, but after doing more tests, I think the number of operations that have to happen in JavaScript are so high that in most cases it's not going to be a thing. I think the browser developers can also minimize this, as well as some of the coin hive type mining by, as they start to update. I think throttling JavaScript back after X millions of instructions, kind of stepping back and being like, okay, look, you ran 3 million JavaScript instructions, let's stop, right? Or at least throttle that back a little bit, and that would also basically mitigate some exploitations. We could also leak module addresses, and this is the one that I'm more worried about. If we're able to leak any module address and find the base address of a module, base address of a DLL, this could be used to go bypass ASLR. Again, I mentioned before, we have a lot of vulnerabilities on the shelf today that they're important and they're dangerous, but we can't reliably exploit them because of address space layout randomization, right? So the operating system developers have done a great job with this, and there have been times when I pulled my hair out trying to figure out how to bypass ASLR in a particular scenario, and sometimes I just can't do it. And I think this potentially can could open up a new era of practical browser exploitation. Right? Time's going to tell on this, but we'll see how reliable some of these leaks become. Right? And again, how well the browser developers, basically mitigate this. Again, one possible way being through the number of JavaScript instructions that are executed. Now, when we get into targeting external processes, and now here, notice in the title of the slide there, I say you have to target a specific external program. Right? And basically the reason is that in order to generate one of these collisions, you have to have knowledge of the actual program that you're exploiting. Because remember, what we're doing here is in that branch target buffer, the BTB, in our attacker process, we're training what we call a misprediction, meaning we're training the processor to always branch on the if when later it should branch on the else, right? And we're training that branch prediction, and again, that's going to go into the branch target buffer. And remember, the attacker, for performance reasons, or sorry, not the attacker, but for performance reasons, the entire address of the branch is not stored in the BTB. Well, in order for me to go and train the processor, I have to know basically which part of the address is stored in the BTB, and I have to know that basically I have to put my branch at the same address as the branch in the other process running on a hyperthread. And if this sounds complicated, it is, right? And we need intimate knowledge of that remote program. I say remote, on that, it's going to be on the same system, but that target program, we have to know and understand how that program is executing. So the attacker is going to have to, study the victim program and understand all of its, basically understand the branch targets and branching addresses to construct an attack. I'm not saying it can't happen. It certainly can. We've seen some trivial proof of concepts. But of all of them, while this concerns me because of the whole recompilation requirements, understand this is going to be the hardest of these scenarios to exploit. So talking about Meltdown versus Spectre, one thing that I've changed here is the note about whether it's remote or local. And as far as kernel memory read, potentially as well, we could indeed, believe it or not, read some kernel memory potentially with that remote process branch. It's unlikely, but again, possible nonetheless. Was it patched? The answer with Spectre is no. And even though Intel says that they've patched, what they're doing is providing the ability, that the hardware, the underpinning for software developers, compiler developers, mostly to go back and patch. Right. So Can you leak arbitrary user memory? Yeah, absolutely. Could it be executed remotely? I think Meltdown probably will be. People have argued with me about this, but I think there are probably some scenarios, and it's going to be special cases, right? But I think there are some special cases where an attacker can do some type of injection, and whether that's a command injection, whether that's I suspect that there are scenarios in which the attackers are going to be able to, or special scenarios in which they're going to be able to execute it remotely. Now, again, in order for them to do that, they have to trick you somehow into running code on your machine, right? So when I say remote versus local, just like when we talk about a browser vulnerability, it's technically remote exploitation. Here, I think kind of the same thing, right? What about Spectre? Yeah, definitely it can be remotely exploited. JavaScript sandbox in the browser, right? So that's a definite remote exploitation there. As far as what's most likely to attack Meltdown, definitely kernel integrity. I think Spectre is going to be browser memory, but don't limit it to that because there are more possibilities. Right? Practical attacks right now, Meltdown is just Intel as far as practical attacks, and Spectre is the whole, basically, the whole lay of the land there, right? Intel, AMD, ARM, custom iPhone processors, etc. So I want to talk quickly about the mitigation. This is not the last hardware bug you're going to see. You're just not. If you haven't been living under a rock, you've probably heard about this whole, how did so many people find it simultaneously, right? The answer is they didn't all find it simultaneously. Right? Well, independent people all found it. Well, yeah, but this whole thing was embargoed for more than 6 months, right? Meaning that the operating system developers and chip developers knew about these problems. And in fact, the embargo wasn't supposed to end when it did. An AMD engineer made an interesting disclosure, right? He talked about one of the reasons why a particular Linux patch wouldn't need to apply to AMD processors. And in doing so, on this open mailing list, basically drew a roadmap to exploiting the vulnerabilities on Intel. And as soon as some people read this and said, "Oh wow," and then combine that with what changed in the Linux kernel, there was a proof of concept out pretty quickly, and that's when everybody collectively decided to lift the embargo, because at that point, somebody's demonstrated a proof of concept, right? Now, we talk about the fact multiple different researchers independently found these, but let's talk about why, right? So you can really trace all of this, I say trace all of this back, but there's a strong tie-in for the people that found this with a Black Hat Europe presentation on the Kaiser patch and KASLR. And I think the name of the paper was KASLR is dead, long live KASLR. So kind of an interesting title, but in any case, some of this, I've heard a couple of the researchers chatting about the fact that they saw the talk, had beer or whatever, hung out together and did their thing and chatted about vulnerabilities and think of this paper almost as a inspiration for more attacks. And again, as people saw this, they independently discovered and said, hey, let's go do some analysis on this. Look, if there was blood in the water before, and the KSLR paper really does show there's blood in the water, my goodness, there's a lot of blood in the water now, right? So I expect additional processor level vulnerabilities to be discovered. And as a result, I want to architect my networks where I start thinking about zero trust in my processor. You may be familiar with this idea of a zero trust network. At this point, I'm starting to think about how do I architect for zero trust if I can't trust my processor. And one of the answers that we'll talk about here really comes down to how we utilize the cloud. Now, look, KPTI has obvious performance impacts. Again, we used to map everything, map all of the memory because it was the smart thing to do, right? Processor microcode patches are likely to have an additional impact as well. Originally, I said testing showed at the time around 10%-ish, but again, there are different workloads, and I mentioned in the original webcast, all workloads are different. You should test yours specifically, right? Now, as you look here, this gentleman who has a PhD, that doesn't mean you're smart, but I am going to give him the benefit of the doubt. He said 20% to 40%, right? And you've got critical machines that are now upscaling loads, and he's saying way more, or way earlier, than they were before. And he says that his Amazon Web Services costs are going to go up by at least 10%, right? This is huge, right? I mean, if you budgeted, if you made design decisions based on, cloud cost models, and suddenly your costs go up by 10, 20, 30%, that's huge, absolutely huge. And he's not alone. I've seen a lot of people griping on Twitter, on LinkedIn about performance impact. Luckily, I have not experienced that, but most of our cloud servers are web servers of one variety or another, and are not under heavy load or exceptionally heavy load, where I would need to go scale up workloads based on a 10 or even a 20% hit, right? But again, you may, if you have something on its last leg of performance, you may find yourself needing to upscale earlier, or you may find yourself, in a physical sense where you can't upscale. If you have just a physical processor, then or bare metal server, you may find a much more significant impact there. So antivirus vendors, this is important to know as well. Microsoft pushed patches. Now, obviously, again, for Spectre, particularly the cross-process branch injection, branch target injection, they can't really patch that in software. But look, the problem here is that because antivirus software runs in the kernel, and because of the way that it accesses some kernel addresses, basically Microsoft saw a number of blue screens in testing and said, hey, we're not going to subject our customers to this. So while you can go download the patch today and may have already installed your patch, know that your antivirus may not be compatible. Now, I've got a link over here for Meltdown patch compatibility. Kevin Beaumont, Gossie the dog, he compiled a list of antivirus patch statuses. And I checked this before I went to press here, and it looks phenomenally better than when I did the when I did the original webcast. But if you go take a look at his spreadsheet he's got out on Google Docs, the thing that really struck me on this is, while the majority of antiviruses are tested now, they're still not setting the registry key. So they've tested and they've declared, yes, we're compatible, but they're not actually setting the registry key. And if you don't set the registry key, even though you patched, the patch isn't being employed. Right? So you've actually installed, the KB is there, but it's not actually being deployed on the system. And I'll tell you how to check for that in a minute as well. You obviously can go check for the registry key, but I've got another link here that you can use to go check the current status of your machine, right? Windows machine at least. Right? So consider systems that won't be patched. I think this is the biggest takeaway for me, besides think about your networks in general. But if you maintain a multi-user environment, and you have servers that won't be patched, think about if you need to re-architect those environments, right? Server 2003, I still know a number of people, a number of businesses, this drives me mad, but they have multi-user environments on a Server 2003 box. They're running critical workloads, and they have users with different needs, different security needs, logging into a Server 2003 box. Well, this is obviously concerning to me. Right? And I'm thinking about ways, it was already concerning because they weren't getting patched, but now I'm even more worried because any user, right, can then elevate to, to system level. Excuse me. Excuse me, there we go. So x86 Solaris, it's easy to say nobody runs that. I have bad news for you, or good news, depending. Lots of organizations run this. Unfortunately, lots of financial institutions run this. And so we've seen a lot of x86 Solaris. People are transitioning off of it, and this may hasten that transition. But I don't know that Oracle has committed specifically when they're going to patch this. And if you've ever worked with Oracle on vulnerability disclosure or getting stuff patched, Oracle tends to do quarterly patch roundups. So it could be 90 days before we see a patch for x86 Solaris. Certainly older versions of OS X. I see some older Mac towers. I see some older MacBooks. Which versions? There are older versions that are not going to get patched, that are out of life cycle, basically life cycle maintenance. Again, you need to think about these multiple workloads with different security requirements on the same physical machine. Right? That's really what's changing here. What about cloud? Look, big cloud providers. Now, look, at day one, I said, the big guys, right? They all did, whatever. I got a couple of comments. People sent me emails, right? I go with a big cloud provider, and they didn't know about it, and they weren't ready. And the whole, I'm talking about Amazon and Azure, right? When I talk about big, right, we're talking about big, right? But look, the reality is that most cloud providers run multiple customers' data on the same physical machines by design, right? That's why they can do it so cheap. But this fundamentally violates my whole don't run workloads with different security requirements model, right? On the same physical processor. Again, this is a spot where, and I'm not telling you to leave the cloud. My company, Rendition, is not leaving the cloud. We will continue to use it because it makes good cost sense for a lot of the stuff that we do. That said, I'm definitely thinking about the cloud, and I'm thinking about what we're willing to put there today that we may have been willing to do things yesterday that we won't today. And I'm going to circle you back around to earlier when I mentioned that I don't think this is the last processor vulnerability. And so now I would ask you, as you're thinking about this stuff, to step back and say, what changes fundamentally do I need to make, right, so that I'm safe for the next one, right? So reevaluate your architecture assumptions, not just for cloud, but in general in your networks, right? Assume that you can't trust the processor. Play that game out. Have that discussion at work and say, hey, if any user that we allow to log onto this machine could elevate to admin immediately, how would we change the game? Right? Browser memory isolation. I think this is super important. On Chrome, you can enable site isolation. There is not a good reason not to do this. Certainly check, certainly do some testing, but go enable this. Hacker Fantastic is the one who originally recommended this, at least that I saw. I think this is phenomenal, and it forces Chrome to load each tab basically into its own process. So even if the same origin policy is bypassed, one site can't steal data from another site. I don't think it's 100% safe. I don't think it's the 100% fix, but it is a 99.whatever% fix. You probably saw some browser cache data in memory and some of your saved sites and some other. But again, compared to the alternative, this is phenomenal. It's exactly what you should be doing. Right. So again, I've got the link here. And by the way, these slides are going to be available shortly after the webcast. I'm going to tweet a link to a PDF of the slides, and of course, they'll be uploaded on the SANS website at some point as well. But if you want them immediately, within 15 minutes, this webcast being over, I'll tweet out the link to the updated slides. So, by the way, if you don't follow me on Twitter, I'm Malware Jake, in case you're looking for the handle there. Look, Spectre. Intel actually outlined several fixes, right, and all the above. But the most interesting one was Spectre. And this requires basically changes to the compiler. And once you change the compiler, you're going to actually have to go recompile your code, right? But I thought it was really cool. Intel actually created a new term, and they call it a retpoline. And a retpoline is a combination between a return and a trampoline. And any exploit developer is probably going to be familiar with this. But basically, what's happening when you execute a ret instruction is it's pulling, the processor is going to pull the address to return to off of the stack. Well, a push places an address onto the stack. So instead of doing an indirect jump or an indirect branch, what we can do then effectively is a push ret. So what you're doing, you're saying, instead of saying jump to an address, you're saying place this address onto the stack. That's a memory write. And then ret says return, which then is going to read that same address you just pushed onto the stack off and jump there. Now, functionally, this is a little bit slower than an indirect jump. That's why compiler developers weren't using this in the first place. Exploit devs are well familiar, pretty familiar with this trick, right? And so are some malware analysts and all that. But this push ret, one of the byproducts of this is it allows you to do that indirect jump while avoiding the training of the branch predictor. So we still do the jump, we just don't train the branch predictor, and that gives us some level of safety there. Right? Okay, so I've got a number of other useful links here, right? Other useful links, and again, like I said, I'm tweet out a set of these. or sorry, again, the link to these slides after the webcast here. There's a great article on the Microsoft blog, Microsoft Security Research blog, about verifying the Spectre and Meltdown protections on Windows. I think this is phenomenal. Now, again, the one variant of Spectre can't be patched without without recompilation, but go check this one out, because I think that this PowerShell script is phenomenally useful to run if you are curious as to whether or not Spectre is executing, whether or not the patches that you installed are actually there. And again, bear in mind your antiviruses in most cases, even if they've been tested and are tested compatible, aren't setting that registry key yet. All right, so you may need to go set that yourself. This allows you to go verify that. There's some thought that you can detect Spectre with performance counters. And CrowdStrike actually did some work on that. And again, I've got the short links here because that's the easier way to go about those than the super long links that, like the Microsoft blog is like 3 lines long when I pasted it in. But Spectre performance counters there basically point you to some CrowdStrike research where they think they can detect exploitation by looking at the performance counters that the operating system tracks anyway. Turns out that in order to do this, you're going to get lots of exceptions, and by getting those exceptions, it's probable that with this high number of exceptions that you're under exploitation. So just some tests that they've done, but interesting nonetheless. You can actually check your browser to see if you're vulnerable to leaking data via JavaScript. I will tell you before you click on that, that actually goes to 10 cent. 10 cents a Chinese site, so kind of be aware of that, right? Risk decision, we're all adults here. I don't see anything wrong with that. It's basically, it looks like 10 cents doing a public service there, but just be aware of that. Also, last week we put together an enterprise action plan at my company Rendition and talked about basically a 6-step plan that you can use to not just for this, but honestly for any big fire drill kind of vulnerability. Now, we do cover some stuff specific to Spectre and Meltdown because it does fundamentally change the way we think about trusting in the processor. And if you want to get into some deep nitty-gritty, some heavy technical walkthroughs, that bottom link there, Spectre walkthrough, I think is phenomenal. And it gets you into some nitty-gritty there and can help you walk through a much more technical. I'm trying to keep it high enough level here that we can go from everybody can have some takeaways, but we can also go from relatively low tech to relatively high tech. Again, this link down here at the bottom is very, very high tech end. And so I want to give you a couple closing thoughts as we close this out. Look, again, I mentioned before, I don't think this is the last CPU attack. So attacks that impact microarchitecture they've been known about for more than a decade, right? This is not new. The idea is not new. Practical exploitation is. In most cases, these were thought to only be exploitable in very, very limited cases, including some physical access. But look, it's clear at this point that these CPU architecture decisions, where we've been engineering CPUs for speed, we need to rethink this, right? And I have no doubt that people way smarter than me at Intel are doing just that as we have this webcast, right? I'm sure they're doing this as we speak. That said, in the long term, you should expect to see more of these. And I think this is particularly going to impact multi-tenant environments, the cloud. All right. I mean, when I say multi-tenant, really what I mean is the cloud. Although, look, we see scenarios where, one of our clients, actually several of our clients that use Linux mail servers, basically for ease of user administration, basically have a user account, and everybody on each user on the mail server has a shell account where they can log into that mail server, unprivileged, but they can still log into the mail server. Well, all of a sudden, this has become a big deal for them because now any user can elevate to root on that mail server. That's huge. We don't want that. So we want to rethink some of these architecture decisions where before we might have gone, not ideal. Now we're kind of stepping back and saying, wow, this cannot stand. So this offers a true wake-up call for us. We're running critical workloads in shared environments like the cloud, again, or if you've got some other architecture decisions you've made where untrusted users can run code on systems where you have high sensitivity data, this is a big deal. So that kind of brings me to the end of my stuff. This is my closing slide here. I appreciate you attending. Certainly let us know if this was useful to you in helping you get a handle on the vulnerabilities. I guess I'll turn it back over to Ruby if we have